Let me move forward with the second presentation that we have, which will be one by Mikołaj Sacha, who is the head of machine learning at Molecule.one. Let me just assign the speaker status to Mikołaj.
Okay. Hi.
Hello, Mikołaj. Just to introduce Mikołaj, he's the head of machine learning at Molecule.one, which, as you will see, it's a very interesting AI company. He's currently a PhD candidate and member of the machine learning group at Jagiellonian University. He's the author of several research publications focused on the topic of interpretability in computer vision, as well as explainable AI for chemical reaction prediction and natural sciences. Let me just give you the presentation. Okay, and as before, if you have any questions to Mikołaj, just type them in the chat. I hand the microphone over to you.
Okay, thank you, Łukasz, for the introduction. And yes, as Łukasz said, my name is Mikołaj Sacha. I am head of machine learning at Molecule.one, which is a Polish startup where we develop AI solutions for chemical synthesis planning. However, my talk today is not about chemistry, but if you're interested in this topic, I'm happy to talk after the conference. The topic of my talk is something that I am also interested in, which is explainability in computer vision. And I would like to present to you this topic and a few approaches about how we can make AI for images more interpretable. So let me start with stating that what is probably obvious to all of us, that we have seen amazing developments in AI, especially generative AI, in recent times. And computer vision models can generate photorealistic images or even pictures that can be considered of artistic value. However, we need to remember that although these models are really impressive, they still have their flaws, and they still can make mistakes. So I would just give some examples. So on the left-hand side, this is a frame from a video generated by Sora, which is a recent video generation model by OpenAI. And Jan LeCun correctly spotted that the generated ant has 4 legs, when our ants should have 6 legs. And on the right-hand side, we have a arguably amusing example where the user asked the model to generate salmon in the river, and we can see a salmon in the river. However, we wouldn't expect salmon in this form in a natural habitat. We would expect salmon looking like that rather on our plate. There are also, sorry, I think I can change the slide. Okay. So there are also less amusing and more dangerous examples of mistakes. So on the left-hand side, this is a screenshot from an experiment where they printed a face of the owner of an iPhone on a mask, and they were able to unblock this phone with this mask. And on the right-hand side, this is a tweet from some Tesla user where Tesla Autopilot sees the yellow moon and considers that the yellow moon is a yellow traffic light, and it keeps slowing down because it constantly keeps seeing this yellow traffic light. And another issue apart from mistakes is that these modern models are so big and have such power to memorize things that they literally can memorize data which can be copyrighted or private. So if by mistake or by some circumstances in the training set of the model, there was some copyrighted data, there is research that shows that you can actually just randomly generate images that look very similar to something that is already there, which is obviously risky for legal, but also for privacy and security reasons. So explaining why models make these mistakes is very important. So first of all, if we know why a model made a certain decision and we know the logic behind it, we can analyze this logic and decide whether it is correct or not. If we understand how the model learned the data, so did it memorize the data or did it learn to generalize, then we can mitigate copyright issues or privacy issues. And also, if we understand in which situations or in which scenario models make mistakes, we can then add some safeguards and, for example, spot situations in which we shouldn't trust the model and spot situations in which it is probably more trustworthy. And as it was already said a couple of times today, neural networks are black boxes, so explaining them is hard. So just to give you an example, AlexNet, which was introduced 12 years ago, so like in ancient times, this was one of the first big models in computer vision, and it already had 60 million parameters inside, so like 60 million numbers. And a more recent example, Stable Diffusion 3, introduced last month, in its biggest version has 8 billion parameters. So now you can imagine that a neural network is like this stack of many layers of matrices of numbers. And if you count all the numbers, then there are like billions of them. And what they do, what are they doing, and how they behave, like what is the reasoning inside, it's very hard to tell. And you cannot tell just by looking at it. You need to do something more. So the question is, what can we do? And as you already know from the previous talks, there are some ways to try to explain the models. And I think in the keynote talk today, it was mentioned that we have some division about what kind of interpretability we can embed or use in the model. And one approach is called post-hoc interpretability. And this approach is about analyzing the model that was already trained. So we have some external algorithm, we have some technique that we can use to take a deeper look into how the model makes predictions. And the second approach, which is complementary, is called intrinsic interpretability, which pertains to developing architectures that are interpretable by design. So we don't need like an external method to analyze the model. The model can just the way it works is interpretable. And as a side note, explainability and interpretability have a slightly different meaning in research, but I think informally we can use them interchangeably, and in the talk I am using them interchangeably. So I want to give you just two examples of different methods. One method will be post-hoc interpretability method. Another method will be a method for intrinsic interpretability. Of course, there are many more methods, but for the interest of time, I will just give you an example of two which I think are quite important. So as the first method, I want to present a method for post-hoc interpretability, which is called gradient-based attribution. And this is actually a group of methods. There are different ways to compute this gradient-based attribution. And the definition is that these methods compute the gradient of the model output with respect to changing colors of pixels. And if you studied calculus, then you probably know what the gradient is. But if you didn't, don't worry, because gradient is just how much modifying y influences x. So in other words, we want to see how much modifying different pixels of the image would change the output of the model. So here's an example for image classification. So the task for the model is to classify whether the image is a doctor or a teacher. Don't ask me why I selected such classes. This is just an example. And you can see that if you give just a picture of a doctor, then the model says, yes, this is a doctor with 99% chance, and teacher maybe with 1% chance. And now what we can do is we can slightly change one of the pixels. So imagine that this green square is 1 pixel. I made it a bit bigger so it's easier to see. but imagine it's just a pixel. And if we change this pixel a bit to a bit more greenish color, well, the prediction for this changed image is different, but slightly different. Doctor has 98% now. So we can say that this pixel has low attribution to the model output. And here is a different example where we changed another pixel to a bit more yellow color. And now you see that after we made this change, now the probability for the class doctor is only 60%, and for teacher is 40%. So we can say that, relatively speaking, this pixel has high attribution to the model output. And you can imagine that we can do this experiment for all the pixels in the image. Yes, so there's a question, how would human determine whether she's a doctor? So the picture is a bit vague, but she has a stethoscope. So maybe you can use that. And teachers usually don't wear stethoscopes, maybe if they are teaching medicine. Anyway, so, but that's a good point. Yeah, she might be teaching medicine. But anyway, let's do this for all the pixels in the image. And if you do this for all the pixels in the image, you get this attribution map. And you can do it separately for all the classes, actually. So you will get two attribution maps. One is for the class doctor, another one is for the class teacher. And don't ask me if this attribution maps make sense. I took them from the paper for one of the gradient-based attribution methods. And as you can see, for some reason, the model considers the head as important if you want to say that the picture is a doctor, and the hands important for considering if it's a teacher. So maybe this actually tells us that there's something wrong with how the model predicts stuff if it looks at such features. A different example, this time for image segmentation. So the model would predict a class for each pixel in the image, and here the model can predict where the dog is and where the cat is and where the background is. And you can draw two different attribution maps for class cat and for class dog. And here it actually looks correct. So when the model wants to spot a dog, it looks at the dog. In order to say that there's a cat in the picture, the model is looking at the cat. So for this model, it's probably it learned more useful features than the previous one. And just to give you like a practical use case, there is this interesting paper where the researchers trained a model for classifying pneumonia based on X-ray scans, and they trained this model, and afterwards they ran this gradient-based attribution on the model predictions. And what they noticed is that the model actually was not looking at the lungs, but was looking here like at the shoulder. So why was the model looking at the shoulder? It turns out that the technicians in the hospital put markers on the patient's shoulder, and these markers were different in different hospitals. And the model learned to recognize which hospitals have more patients with pneumonia. So this was a really interesting finding that was made possible because of these methods for explaining what is the part of the image that is important for the model. Okay, and if you want to read some papers, then here's a list of some important methods for gradient-based attribution. These are papers for machine learning, so in order to understand it, you need to understand some theory. So if you're interested, you can take a screenshot and take a read. Okay, now let's move to the intrinsic interpretability. So in post-hoc interpretability, we took a trained model, analyzed maybe inputs, maybe some parts of the model, but the model itself was unchanged. And in intrinsic explainability, we actually modify the model itself. So we add some special layer, or we somehow design the architecture that it is more explainable. And I want to give you, sorry, do I have this problem that the slide is super small? Or do you see the slide correctly? Okay.
It was super small.
Okay, but now it's fixed. I don't know what happened. Okay, so one method for intrinsic interpretability, actually this is something that I'm working on my PhD, is called prototypical part-based methods. So imagine we have a model for classifying different species of birds. For some reason, this is an example often used in the literature. So here, the model says that this is a bird called clay-colored sparrow. And in the normal image recognition model, this is the answer you would get. But with this prototype-based models, the model can tell you why this is a clay-colored sparrow. And it tells you this is a clay-colored sparrow because it has these different fragments, which are in yellow bounding boxes. And these different fragments actually look like fragments that I have already seen in the training set. So the model says this is a bird of a given species because it has a head that looks similar to a head of the species that I know from the training set, and I can show you this head. And it has a wing that is similar to a wing that I have seen in the training set, and I can also show you this wing that I know from the training set because I have it saved in my memory. So how does this model do that? This is a picture of the model architecture. You don't have to understand it. I'm not going to go into details, but there are 3 things to remember about this model on a high level. So first of all, backbone of this model is like a standard image recognition model called convolutional neural network. So actually, the most of the architecture is like a normal model for computer vision. However, there is this special layer which is called a prototype layer, and this layer learns prototypical parts that corresponds to different classes, and they are not hard-coded, they are not defined by humans. The model, when it is trained on large data set, it finds fragments that define different classes. So it can, in this example of birds, find different parts that are characteristic for different species. So yellow wing can be characteristic for one type of bird and red belly for another type, for example. And in the final layer that gives you the prediction of the class, the model will actually do sort of a voting where it compares fragments of the input image to all of these prototypes that it is also learning. And based on the similarities, it will say that, yes, this is a, let's say, black-footed albatross because it has this fragment which looks like this prototype of black-footed albatross, and it has this other fragment that is very similar to another prototype of this class. And based on this voting, the model gives you prediction. So as you can see, this is definitely intrinsic interpretability, where the model makes decision using the explanation that we wanted, that we want from the model. And one a bit more practical example, although it is also from literature, is about how we can use this prototype-based networks. So here, the researchers actually added the human in the loop. So the model was trained in several stages, and after each stage, there was a human intervention. And the human who did these interventions, after each stage of the training, the human decided which prototypes are good and nice and explain the reasoning nice, and which prototypes should be thrown out. And the prototypes selected by the human were removed, and then next stage of the training was run, and so on and so on. After finally it was stopped after a few such iterations. So it turned out that, as you could expect, it increased the explainability of these prototypes because they were manually selected by the human, and also the architecture of the model allowed for this intervention. But what was a surprising finding is that this actually also improved accuracy of the model, which might not be expected, but it kind of works for these types of models. Yeah, so these were two examples of explainability in computer vision that I want to give. Oh, sorry, there is also a slide about prototype-based models. So if you want to read about prototype-based models, probably the paper to start with is this Protopinet. But again, these are for the people who like machine learning. And yes, so in summary, modern AI systems for computer vision, although powerful, can make mistakes. Deep neural networks are black boxes, as we already know from the previous talks, and their decisions are often hard to explain. And there are post hoc interpretability methods which you can use to explain the predictions of some model that's already trained. And one example of such group of methods is gradient-based attribution. And there are intrinsic interpretability methods that are interpretable by design. An example of that would be prototype-based models. And understanding when these models make mistakes is very important if you want to improve them and understand their failure modes, which is given in these examples, two examples, but obviously there are many more examples for this. So this concludes my presentation. So thank you for listening. And I think there are some questions, so I can answer them.
Mikołaj, thank you for the interesting lecture. We have some questions. So what tools do you use to get such heat maps? Is this part of Azure AI Vision or is it another group?
Yes. I'm a machine learning engineer, so I do this all by myself, writing Python code. So I cannot tell you, to be honest, if the platform like Azure that do things more automated allow for this. I haven't used them myself. But I know there are libraries in Python that you can use to easily generate such explanations for already trained models. But you would need to do it yourself and know how to set it up on your computer. But yeah, I don't know if there are some tools like that on some cloud platforms like Azure or AWS, to be honest. Sorry for not being informative here.
We have a question, but I don't know if I properly understand it. Is it CAPTCHA used for those learn purposes, man in the loop? But
oh, you mean like CAPTCHA, like the CAPTCHA that you do on the internet? Yes. So not in this particular example. This was just an example of an experiment when they used human to make their particular model better, and yeah, it was not about using CAPTCHA input. However, as far as I know, and I don't know because I don't work in Google, they use inputs from CAPTCHA to improve their models, and that's also one of the reasons why you rarely see CAPTCHA. I mean, you see it, but CAPTCHA, which is about image recognition, is relatively easy to solve by modern AI systems. So I think like currently the state of the art is that the CAPTCHA that tracks your cursor is actually better as of now. So the one when you just need to put cursor in a box, but yeah, probably in the future it will also be solved. So I think like judging from how CAPTCHA has been changing over time, I think that definitely yes, this data is used by the companies that develop CAPTCHA systems. But I cannot say for sure.
Okay, so I would have one question to you. So because you work at Molecule.one, and you work on a very specific use case where you apply a thing called graph neural networks to predict chemical reactions and some physical properties. And graph neural networks are a big thing, even though they may not get as much attention in everyday life. Could you tell us a bit, just a few things about your work and how you use graph neural networks?
Okay, thank you for your question. Yes, so I decided to focus on some topic that is closer to the general audience, which is computer vision. Chemistry is more specific, but definitely AI in life sciences, in biology, in pharmaceutics, in chemistry is something that is developing and is improving and is really important. There is a usage of graph neural networks, obviously, because you can represent molecules as graphs, and you can predict properties of molecules. You can predict whether the molecule is easy to synthesize or if it's toxic or not. So we use graph neural networks for that. I think that explainability in chemistry, in AI for chemistry, is actually also really important. So that might be interesting for people at this event. That if you use your model, if the user of your model is already a skilled scientist, like an organic chemist, you really need to prove to them that it works, and you need to prove to them that the model has some reasoning behind the predictions. So, for example, when you predict whether a chemical reaction would succeed or not, you want to give some examples of reactions from the literature that are similar. So, yes, explainability is also very important there. And there's whole topic of explainability in graph neural networks. And actually, the prototype models are also applied in graph neural networks. But that would be a topic for a different talk, I guess.
Okay, good. So thank you very much for your talk, for all these examples of how we can explain the reasoning that AI does to when it does machine vision. Thank you again for being with us today. And now we are switching to our last speaker.
Thank you.
Thank you very much.